Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on Foundational Mathematics, what we are going to try to discuss right now is, the infinite series, in which you are taking infinite sums. So before we get started, please consider liking and subscribing, and also please check the notes in the description for the notes throughout this entire discussion. So before we get started, I will set up the timeline that you are able to skip through. So first, what we will do is that we will introduce the topic of infinite series. So it's introduction, and then we have some tests for convergence, and finally we will also discuss the power series. So let's first discuss about the infinite series. So before we go to the infinite series, we'll just think of a finite series or a sum of a sequence. So the sum of a sequence will be defined as Sn, and it's defined to be the sum from n equals to 0 until n of an. This definition could be substituted with n equals to 1 if let's say n equals to 0 corresponds to a value in which it is not definable. So you could just use n equals to 1 instead. So in this discussion, we will be discussing about positive and decreasing sequences. So if it keeps on going up, I won't consider it because it's gonna diverge anyways. And also, I won't be discussing about negatives because negatives means that you are also subtracting, but I will later have a small discussion about it. So for a series to converge, or when n goes to infinity, it will approach to a value. So the way that you could write this is that the infinite series subtracted by Sn will be less than the epsilon, where epsilon is a value. And so this pretty much tells you that you could always find an n which is pretty large, such that if you actually compare the infinite series subtracted by a series until a certain value called n, it will be less than the error function. So in here, n epsilon literally corresponds to the amount of value that you need to approach to that value's error. And if you go above it, it will be much more smaller, which does make sense. So let's just do one type of infinite series, and we'll call this as the geometric series. So the geometric series will be Sn will equal to the infinite sum from n equals to 0 until n of r to the power of n. So this is 1 plus r squared plus blah 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 until r to the power of n. Now the question is, what's the sum of this star series? Well, if r is greater than 1, what we know is that it's gonna diverge, and r equals to 1 will also diverge. So we'll just consider when the r is less than 1, which is greater than 0 anyways. So if we try to figure out the sum, you could just multiply both sides by r because r is not 0. So r Sn will be the same thing as the sum when n equals to 0 until n of r n plus 1. So this will be the same thing as r plus r squared, blah blah blah, r to the power of n plus r to the power of n plus 1. So you could subtract this guy and this guy, so you would get r minus 1. Sn will equal to r to the power of n plus 1 minus 1. So you could write the Sn to be Rn plus 1 minus 1 over R minus 1. Now, if n approaches to infinity, this top value here will get approach 0. So as it goes to infinity, for this particular case, it's going to be 1 over 1 minus R. And this is the infinite series for a geometric series. for a geometric sequence. So we could just check it by actually plugging in the definition of the convergence of a infinite series. So 1 over 1 minus r, subtract that by 1 minus r to the power of n plus 1 over 1 minus r, which comes from the Sn for a particular n. And then we try to compute this. What we will get is r to the power of n plus 1 over 1 minus r. And for any epsilon, you could always choose an n which is very big so that it will be near epsilon. Because as you know, r to the power of n minus 1 will pretty much approach to 0 if r is less than 1. So after the discussion of the definition of convergence, I will introduce some tests for you to actually determine whether a series is convergent or not. So let's do this very simple idea. If you have an to be smaller than or equal to bn, you could get a certain clue whether the series diverge or converge depending on the other. So let's say if the infinite sum of bn goes and converge, you could also know that an should also converge. This is a very logical statement. So if you have like this type of graph, and then you have this type of graph, so this is a bn, and this is an. You could, if the bn sum is convergent, that means that an must also be convergent. But if an is divergent, so if an is diverging, you could conclude that bn also diverges. So let's do a certain example of this test. If we just write 1 over n squared, and then we ask, does this converge? We could just write this down as 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 and blah blah blah. And a fact that we could use is that this is smaller than or equal to 1 plus 1 over 4 plus 1 over 4 plus 1 over 16 plus 1 over 16 plus 1 over 16 plus 1 over 16, and then later on it will be 1 over 64. So this pretty much concludes that this is the sum of 1 plus 1 over 2 plus 1 over 4 plus blah blah blah. So this is the sum of 1 over 2 to the power of n. And you know this to be the sum of half to the power of n. So this thing converges to 2. And so this means that your 1 over n squared should be less than or equal to 2. This is a fact that you need to know. Is that if you know one function is convergent, you could know that the other function is also convergent. Let's do another example. We will just say that we want to figure out does the sum of 1 over n converges or not. So this could be written as 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and etc. So you could rewrite this as something greater than equal to, sorry, this should be less than equal to 1 plus half plus 1 over 4 plus 1 over 4 and etc. What you could conclude from here is that if you sum them up, you could get 1 plus half from 2 times 1 over 4 plus another half, which comes from 8 1 over 16ths, and so on. So this will correspond to 1 plus the sum of half. And this diverges because obviously if you add the same number again and again, it will diverge. So this diverge, which means anything above it will also diverge. We could also use the same information of, let's say, we know that n is greater than square root of n when the n goes to infinity. So this means that 1 over n is smaller than 1 over the square root of n. And so because this thing diverge, we know this thing will also diverge. So there's lots of there's lots of these examples that I could show you, but the easiest way for you to actually to find these examples is by looking at the textbook, or you have some experience about it. And so this type of test is very it your brain must be very creative for you to find a series which is convergent or divergent, or you could just look it up from a list and try to compare it with your own function that you have. So that's a type of test, but it's very it is it doesn't have a very good step for you to figure out if something is convergent or divergent. So that's why I will propose the ratio test. So the way that you use the ratio test is by actually first figuring out what exactly is the ratio test does. So if you have a geometric series in which an equals to an plus 1, well, it's r times an equals to an plus 1. That's the definition of a geometric series. And as you know, if r is less than 1, the function will be convergent. And that's the idea. So you could just take the ratio of an plus 1 over an, and if this is less than 1, this will be convergent. While if r equals to an plus 1 over an is greater than 1, it will diverge. So if you extend this idea towards actual functions, you would actually see why this is a very useful information. So even though if the functions at the front of this, so when n is pretty small, you could still compute about it, and it is not really having a ratio. But if you go further and further, as long as it's decreasing, there would be some form of a ratio going on. And if the ratio is going up, it means that it's diverging, obviously. But if it is going smaller and smaller, it's converging. It is the same logic as a positively decreasing function. So let's give a certain example. So one of the easiest examples for us to check is 1 over n squared straight away. So if we try to check 1 over n squared, it will be 1 over n plus 1, everything squared, divide that by 1 over n squared. And this will correspond to n squared over n squared plus 2n plus 1. And this is always less than 1, because as you know, this value is always bigger. So therefore this is convergent. So the ratio is near 1, but it's not exactly 1. There's always a value less than 1. But what if the value is 1 over n plus 1 and 1 over n? Could we try to compare this? N over n plus 1. So one example that I will be taking will be n over 3 to the power of n. It's a very stray example, but this is where the idea comes in. So if you try to compute the ratio, it's going to be n plus 1 over 3 to the power of n plus 1. Divide that by n over 3 to the power of n. This means that it will be n plus 1 over 3n. Now, the fact is that when n goes to infinity, you could ignore the 1, and then the n's will later cross out, turning this out to be 1 over 3, which is always less than 1. So this concludes that the ratio is always less than 1 for very big values, meaning that you could pretty much almost fit it with a geometric series and figure it out that the infinite series converges. But certain informations couldn't be truly be figured out only from the ratio test. Something like 1 over n will give you 1 over n plus 1 over 1 over n, which is n over n plus 1. And this is in general is always less than 1. But if you go when n goes to infinity, it is as if this value doesn't even exist. So the value is going to be approaching 1, which is not allowed. You don't know if it's diverging or converging. And this is a very harsh fact that if you know that the ratio will go to 1, you couldn't truly get any type of information from it. So a much more powerful tool when you're doing a infinite series check is the integral test. And this is a very simple test. If you have a integral here from one point to another, remember the definition of a integral. It's summing up small sections. And you could be summing the big part, something like this. So there's always overhangs, like so. Or you could be measuring its unders, something like this. There you go. So you could see that the sums are bounded. So we know that the integral of your function n with respect to dn from 0 to infinity, because we're going to infinity, is pretty much bounded. So the value is going to be less than the sum from 0 to infinity of your function n. As you could see here, if you sum it up from 0 to infinity, the values will have lots of overhangs, meaning that the value wouldn't go above this discrete summation. But also it couldn't be less than the discrete summation from 1 to infinity of your function n as well. So let's give you some use of this. So let's say I want to figure out the function n from so it's the sum of 1 to infinity of function n. And the question is, does this diverge or not? So you could just use the definition that I have already give here. So maybe we could just start from 1 towards infinity. So the integral from 1 to infinity of function n dn. And so this function n here technically should be 1 over n. So let's try to figure this out. And so if you try to plug it in towards your integral from 1 to infinity of 1 over n dn, this is going to be natural log of n from 1 to infinity. And this is divergent, because if you put in your infinity in, it will explode to infinity, which means that this sum is divergent. And so because of the integral from 1 to infinity of fn is divergent, means that the sum of 1 over n must also diverge. So this is just a comparison check, but instead of using other series, you're using integrals. Let's do another one. Maybe 1 over n squared. So for 1 over n squared, we will check from 1 to infinity of 1 over n squared. And I want to know if this is convergent first or not. So we could try to check the integral from 1 to infinity, 1 over n squared dn. This is going to be negative 1 over n from 1 to infinity, which means this will go to 1. So this is convergent, meaning that you could actually get the sum from 2 to infinity of 1 over n squared to be convergent as well. But what we want to figure out is the sum from 1 to infinity. So why does the sum from 2 to infinity give you an idea? Well, it's because if you put 1 into the if you want to change this into 1, you could transform this into this as 1 plus the sum n equals to 2 to infinity of 1 over n squared. It's the same idea. So this means that the 1 over n squared is also convergent. So there are lots of examples of using the integral test, and I think the integral test is one of the best ways for you to check whether a function is convergent or not. But finally, there is another type of test that you could use, which is called the absolute convergence. So this is a very simple idea in which you could use this for negative of increasing or decreasing. So it could be negative, positive, increasing, decreasing, you name it. It will always work, because what you do instead is this. You just take the sum of the modulus, and then you check if it is convergent or not. If it is convergent, it will be called as absolute convergence. And this gives you an idea that your function, that your series without the absolute value is also convergent. And let me tell you why. So if you have the graph here, and let's say we are doing the integral test, if the absolute convergence does something like this, means that you could actually do the negative and do the same thing. And because of the plus and minus conflict, your series will be always in between these region, meaning that your infinite series will be bounded between these two extremes. But if it is not absolutely convergent, but if you do the sum, it converges, it is something that you call as conditionally convergent. So something like 1 minus half plus 1/3 minus 1/4 is conditionally convergent. And this is because of something like this. Think of it like this. You could try to take the sum of 1 over 2n minus 1, and then you take the sum of 1 over 2n plus 2n. N equals to 1. This is n equals to 1, yeah. So if we try to do this, this goes to infinity. This goes to infinity, but you're subtracting infinity with another infinity. So it doesn't actually work. But you could do the sum and figure out that it is actually convergent. And this is what you call as conditionally convergent, because the way that you sum up the infinite series determines the end result. But if it is finite, it will have a particular value. And this is very interesting. So this is the idea where some infinities are greater than other. And so you couldn't really say infinity minus infinity is always 0. It could be 1, it could be 2. It really depends. So because infinity is just a concept, we couldn't really use it to do computations. So this is why this is called as conditional convergent. So lastly, I want to talk about the power series. So in here, I'll be discussing power series and x. So x will be our function. And so what exactly is the power series? It's a very simple idea. So it's just s equals to the infinite series of an times x to the power of n, when n equals to 0 towards infinity. And this should be something that you're familiar with. So this is one expression of Taylor series. So Taylor series is one type of power series, but there are lots of different types of power series. You could have it not really form as like the Taylor series. It could be some other types of series, but normally you use it for the Taylor series because every single function has their own Taylor series. And that's the same idea. Every single function has their own power series, which is normally the Taylor series. So why do we discuss about the power series? So I want to talk about its radius of convergence, in which it is where your series will converge. So let's say if you have this s here to be convergent, meaning that you have an r. So r is like your multiplier. And doing the ratio test, it's an plus 1 xn plus 1 over an xn. So this will be an plus 1 over an, multiply that by x. And if this value is less than 1, we call this as obviously a convergent series. But if it is greater than 1, you call it as a diverging series. So pretty much this x here could be any type of value, as long as it forms the small r to be less than 1. So we could just state what the magnitude of x must be. If it is less than an over an plus 1, meaning that it will be much more smaller, means that it will be convergent here. So this will converge. But if your magnitude of x is greater than an over an plus 1, you would call this as divergent. And this is what you call as the radius of convergence. So these two things here are called radius of convergence. Radius of convergence. And this inequality shows you the interval of convergence. So we could do some tests. Let's say the e to the power of x, the one that we have already defined multiple times. This is the sum of 1 over n factorial times x to the power of n. So this infinite series, if you try to find the radius of convergence, the magnitude of x will be less than 1 over n factorial over 1 over n plus 1 factorial. And this will be n plus 1. And so if n goes to infinity, this will go to infinity, meaning that the radius of convergence is infinity, meaning that it spans throughout the entire number line. So the series is viable for every single point. But let's say if you have a certain function, let's say 1 over 1 minus x. So this turns out to be 1 plus x squared and blah blah blah. Or this is the sum of x to the power of n. So if you try to check this infinite series, what you would have is this magnitude, the radius of convergence is 1. So this power series is only viable when x is in between -1 and 1. So this brings me to my final conclusion for the power series. Here's the fact: if you have fx equals to gx, the infinite series an must be the same thing as the power series bn. They have to be the same. Second, if you take the derivative of 1, if you take the derivative of x and the derivative of g, you would have the same function. So a prime n and b prime n, they should have the same series again. And the same thing for integral, even though there's a constant that's differing, but the power series must always be the same. So this gives you a very useful information when you're doing equality of different functions, is that you can just expand it in terms of the power series, combine them all, and then trying to figure out if it's convergent throughout the entire range. And then you compare the same coefficients, and it turns out that everything is the same. It means that one function is the same thing as the other function. Something like if you do sine squared of x is equal to 1 minus cosine squared of x, you could do this power series expansion, try to figure out where is the radius of convergence, and try to compare each of the components. And so that means that you know that it is viable when x goes from one point to another. So this is where I'll leave the idea of infinite series. So this is very useful if you're doing, let's say, integrals, or you're doing computational maths. So if you're trying to compute a integral but you don't know if it is convergent or not, you'd be doing the integral first and then checking if it's convergent or not, and then you try to do it with a computer that does an infinite series, or pretty much a summation towards n, in which n is pretty large. So there are lots of uses of this, but I won't fully discuss about it in here. So that's all for this video. So thank you very much for watching, and make sure to like and subscribe, and also please share this to your friends who really need to understand the mathematics behind physics in a much more deeper understanding. So thank you very much, and I will see you on the next video.